Did you guys do anything exciting in class today? Yeah. Oh, we'll continue on. Well, let's look at some of these combination questions. So here we go. How many ways are there to form a group of 3 people from a group of 7? The word I would typically use here is choose, meaning we're asking how many ways we can choose 3 people from 7. In fact, right, there's exactly 7 of us in this room. So it's the number of ways we could pick 3 different people, right? You 3 or you 3 or 1 2 3 or 1 2 3. Right? There's a lot of different ways. How many ways? Well, here's what I would write. I would write 7 choose 3 like this. That's my preferred notation. Hopefully that's how he's writing it in class, but if he's not, it's also fine. That's going to be 7 factorial divided by 3 factorial times 4 factorial. Again, I'm always thinking of these numbers showing up and then the difference between them showing up, right? That's right. The bottom things out of the 7 essentially. So usually you can just leave your answer like this, but if it's small enough, you often want to simplify. Like that is an answer, but it's not super meaningful in that I don't actually know what the value is. So let's actually simplify it. 7 times 6 times 5 times 4 times 3 times 2 times 1, which I'll just write as 4 factorial over 3 times 2 times 1, also times 4 factorial. Those are going to cancel. Whenever you do this, the answer should be an integer, right? The number of ways of picking 3 people from 7 people, there shouldn't be like a fractional way of doing that, right? It's a whole number answer. The 6 divided by 6 cancels, and you just with 7 times 5, which is 35. So there's 35 ways we could pick 35 distinct ways we could pick 3 of us. Just to contrast that with the other thing we were talking about last time, which was permutations. If on the other hand, I asked how many ways can we pick a president, vice president, and treasurer? Well, then it matters what order we're picking the 3 people in, right? It's not just we pick, Alexa, Nathan, and myself, and that's good. We also have to describe between the 3 of us who's going to be what, and there's 3 factorial ways of doing that. So in this case, the answer is a permutation, which there's not good notation for, like p of 7 comma 3. It's just 7 factorial divided by 7 minus 3 factorial. I wouldn't write it this way. I know I just wrote it that way, but really what I would do is I would just think about it as, okay, great. There's 7 choices for the president, then 6 choices for the VP, then 5 choices for the treasurer, which is 7 times 6 times 5, which is going to be, I don't know, 210. Notably, it's this previous answer multiplied by 3 factorial, or 6, right? That's 35 times 6, which is 210. You're just taking the number of ways you could pick any 3 people, the multiplying it by the number of ways you could arrange or order or pick the spots for each of those 3 groupings of 3 people. And there's 6 ways to do that for any grouping of 3. A more interesting question, maybe, back to the committee or the group of 3 people. What if for our group of 3 people, there are 2 specific people that cannot be in the same group, that cannot be in the group together. How many ways can we now make a group of 3 people that doesn't include these 2 people together? Well, there's a couple ways to do this. Here's probably the easiest way. Let's call those 2 people A and B. So we've got A and B, and then let's call everybody else 1, 2, 3, 4, and 5. We know from the work we just did in part A that there's 35 ways of making groups of 3 people. But some of those ways are going to include something we don't want, namely A and B together. How many different groups of 3 people have A and B together? Well, I can have A and B in 1, or A and B in 2, or A and B in 3, or A and B in 4, or A and B in 5. So it looks like there's 5 groupings of 3 that have A and B together. So there are 5 groupings of 3 people that would include both A and B. So if we want all the groupings of 3 that don't have A and B together, we take the 35 ways of grouping any of the people together, and we subtract the 5 ways of grouping the people together we don't want. So our answer here is going to be 35 minus 30. 35 minus 30. 35 minus 5, which is equal to 30. So often a way of attacking a problem isn't trying to figure out what you want, it's trying to figure out what you don't want and then taking that away from the stuff you do want. Often the battle with a lot of these problems is figuring out how to think about getting the things you want. Let's look at more examples. Or also, I should say, if there's questions along the way, you should ask. You're welcome to ask questions. There's something else I want to say there. No, I don't. Yeah, question? No, the first one's a combination. This is specifically the choose function, which is for combinations. Choose function for combinations, where we don't care what order we pick the 3 people in. We just care that we pick 3 people. Say that one more time. Sure. So 1C is building off of 1A. So we're saying, how many ways can we pick 3 people in a group out of 7? But there's 2 people that can't work together. So maybe you and I, we can't be in the same group. So you can pick like those 3 or those 3, but not you and me and Alexa, or you and me and Blanca, or you and me and anyone else, right? So the idea is to count all the ways of getting the thing that we want. So we want groups of 3 people, which we know there's 35 ways of picking 3 distinct people from 7 people. But then we're going to subtract off the ones that include where person A and person B happen to be in the same group. And there's only 5 ways of doing that. You can have A and B in 1, or A and B in 2, A and B in 3, A and B in 4, A and B in 5. Those are the only 5 ways that you get A and B together along with some other person. So we don't want those 5 ways. So we take the 35 ways that we said were ways of grouping 3 people together, and then we're taking away the 5 ways of grouping 3 people together that we do not want to include. Good. There's probably another way you could have come up with this. This is probably the most like direct way, but you probably could have said something like, well, if I don't want A and B together, yeah, you could, so just as a point, just to point out that there's multiple ways of attacking problems like this, another way we could have answered question C here is you could have said, okay, well, we have persons 1 through 5, and then we have persons A and B. And if you want a grouping that doesn't have both of A and B, but does have, yeah, but can have at least one of them, well, there's a couple ways you can do that. You can either say, I'm going to pick 2 of these folks. Cool, there's 5 choose 2 ways of doing that. Times 1 of these folks. There's 2 choose 1 ways of doing that. That equals, let's see, 5 choose 2 is 5 factorial over 3 factorial times 2 factorial, which ends up being 5 times 4 divided by 2, which is 10. So I made it, not a mistake, but I've written something inappropriate because I forgot to multiply by the 2 choose 1 here. Times 2. Important to recognize, worth recognizing. 2 choose 1 is just 2. The number of ways of picking one person from a group of 2 people, there's 2 ways. Anything choose 1 is always going to be that number. 5 choose 1, the number of ways of picking one thing out of 5 things is, well, there's 1, 2, 3, 4, 5 ways I can pick one of my 5 fingers. So anything choose 1 is just that number. So 5 choose 2 times 2 choose 1 is going to be 2 times 5 choose 2, which is going to be 20 divided by 2 times 2, which is going to be 20. Wasn't the answer I got? Oh, I forgot something, right? I don't have to have person A or B. I could have just 3 of these folks over here. And 5 choose 3 is also equal to 10. You can even say it's 5 choose 3 times 2 choose 0. I want 3 of these folks. I want none of those folks. So let's actually do the math, even though there's something else we should say. So 5 choose 3 is 5 factorial over 3 factorial times 2 factorial. And 2 choose 0 is, this is actually where the 0 factorial thing I mentioned earlier is important. 2 choose 0. So let me ask you, this is going to sound kind of stupid. Let's talk about 5 choose 0. How many ways are how many ways are there of picking 0 of my fingers? There's one way. I can pick none of them. Right? Which sounds kind of weird, but it's true. Right? It's kind of like, a better example is if you're flipping coins. If I was flipping 2 coins, how many ways are there of getting 0 heads? Well, there's one way. I get 2 tails. There's also a couple ways of getting a head and a tail, right? You can get 1 head and 1 tail, or 1 tail and 1 head. And you can also get 2 heads. So, right, you can get 0 of a thing. And there's usually one way of getting that. You get all of the other thing. So 2 choose 0 is 2 factorial over 0 factorial times 2 factorial. That better not be division by 0. That's why we had to say earlier that 0 factorial is defined to be equal to 1. So we don't run into problems. So this ends up being, again, 5 times 4 over 2, and then times 1, which is 10. And look, 20 plus 10 is 30. The number we came up the other way we approached the problem. As an other worthwhile note here, in fact, let me just write these things down. So generally, it's good to know that n choose 0 is equal to 1. Any number choose 0 is 1. N choose 1 is equal to n. The way you can pick one thing out of n things is n different ways. And then there's also a nice symmetry property. You actually are seeing it right here. 5 choose 2 and 5 choose 3 are both equal to 10. That's 10, that's 10. Because the number of ways of picking 2 of my fingers is exactly equal to the number of ways of not picking 3 of my fingers. So if I want to count the number of ways to pick 2 fingers, I can also count the number of ways to pick 3 fingers and then exclude them. So 5 choose 2 is equal to 5 choose 3. Or you can also say something like, I don't know, 7 choose 2 is equal to 7 choose 5. Or more generally, n choose k is equal to n choose n minus k. There's always a symmetry. And while we're here, we might as well point out the really cool thing, I think. These numbers, these choose numbers, are more generally known as the binomial coefficients. So you may have seen someone, maybe me, mention something called Pascal's triangle, or you may have heard of Pascal's triangle, which starts off like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 1, 1, 5, 10, 10, 5, 1, and so on. We just keep adding things to the next number. Well, I'm kind of doing a disservice because really what we have here, I guess that's 0 choose 0. So really these numbers are 0 choose 0, 1 choose 0, 1 choose 1, 2, choose 1. Sorry, 2, choose 0. 2, choose 1. 2, choose 2. 3, choose 0. 3, choose 1. 3, choose 2. 3, choose 3. And it just goes on and on and on. Every number in here is really just some number, choose some smaller number less than or equal to it. Same thing. 4, choose 0 is 1. 4, choose 1 is 4. 4, choose 2 is 6. 4, choose 3 is 4. 4, choose 4 is 1. And it goes on and on and on. It's kind of cool. I think it's really cool, actually. Yeah, anyway, so if you're ever trying to find, like, I don't know, that's not. You could draw Pascal's triangle to find the number, but really you don't have to, right? You could just use the formula that, once again, I'll write it down, that n choose k is n factorial divided by k factorial times n minus k. Which is why this ends up being the same, right? Because n choose n minus k is really n factorial over n minus k factorial times n minus k factorial. But n minus k is just k. So they're the same. Cool. All right, let's do more examples. More examples. Oh yeah, and the attendance form. I forget. I think you got the very possibility. You didn't pass on the attendance form. Like, oh my god, I'm sorry, I forgot. And they were like waiting. So then really wanted to leave before I had done it, but I forgot. So let's see. Here's this next situation. 2. We got a jar. Jar contains 5. Let's use colors here. 5 green, 4 red, and 3 black marbles. We randomly choose or select 3 marbles. I'll point out that we didn't say anything about whether we're putting them back in or not. If you don't say anything, the assumption is it's without replacement, meaning you take a marble out and you don't just put it back in. So we randomly choose 3 marbles without replacement. We're not putting them back after each choice. How many ways are there to get following? All green. Well, how many ways can we pick 3 green marbles? It feels like a weird question in the beginning. You're like, well, there's only one way to get 3 green marbles. They're all green. But the thing is, there's 5 different green marbles. Maybe they don't look exactly the same. We don't really care. But for those 5 green marbles, there's not just one way we could pick 3 of them. There's 5 choose 3 ways we could pick 3 of them. If we want all green marbles, it's going to be 5 choose 3. We pick 3 of the 5 green ones and none of the other ones. Now, I will point out, you don't need to write the next part, but I'm going to write it anyway. I wanted 3 of the green ones. I wanted 0 of the 4 red ones and 0 of the 3 black ones. It's kind of like putting a 1 in front of an x, or when you take the derivative of a function of x, multiplying by the derivative of x, which is 1, using the chain rule. Unnecessary, doesn't change the result, but good to think about for the larger context. So here, going to be 5 choose 3, which we've done enough times now to know that it's going to be 10. 5 choose 3, 5 factorial over 3 factorial, 2 factorial, times 1 times 1. This number here. So when I'm simplifying this, here's what I'm doing. I'm thinking about 5 factorial being 5 times 4 times 3 times 2 times 1. I'm not writing this step, though. I'm not writing 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. I'm canceling out the larger factorial in the denominator, the 3 times 2 times 1 with the 3 times 2 times 1 up there, and then just writing, oh yeah, it's going to be 5 times 4 I'm going to stop after 4 because everything after 3 is going to get canceled. And then on the bottom, 2 times 1, and that's going to be 20 over 2, which is 10. That's how I would. So I would go from this to that there. Again, as long as the numbers are small enough. How small? Good question. I don't know. Certainly less than 10. Probably. There's not a really good, like, there's not a good answer to how small. Okay. What about all black? Well, there are only 3 black ones. So there's only one way of choosing 3 black ones. You pick the 3 black ones. There's 3, choose 3 ways of doing that, but 3, choose 3. Or how many ways can you pick 3 things out of 3 things? There is one way of doing that. You could also write the formula. I don't think you need to write the formula, but the formula would be 3 factorial over 3 factorial times 0 factorial. Again, showing us why we need 0 factorial to equal 1. So that's going to be 6 over 6 times 1, which is just 1. Sure. More interesting questions. How many ways can we get 1 of each color? Okay. Well, how many ways are there of picking 1 green marble? How many green marbles are there? So there's 5 different ways I can pick a green one. How many ways are there picking a red marble? How many ways are there picking a black marble? So it's going to be 5 times 4 times 3. I'm just writing it in the notation that's a little bit more purposeful here. It's 5 choose 1 times 4 choose 1 times 3 choose 1. That's just going to be 5 times 4 times 3, which is 60. How many ways of picking no green marbles? Well, how many marbles aren't green? 7. Out of the 7, how many do I want to pick? Not 7. We're always picking. So the problem, we're always picking how many? We're randomly picking how many marbles? 3. We're always picking 3. I haven't changed that part of the problem. So there's 7 choose 3 ways of doing that. Basically, when you're doing these kind of problems, you're saying how many ways of getting these things. It's okay. How many of the things meet the criteria? In this case, there's 7 of them. There's 4 red, there's 3 black, there's 7 total non-green marbles. And of those 7, I'm trying to get 3 of them. So I do 7 choose 3. But it's always kind of what are the things I want, and then how many of them do I pick? That's going to be 7 factorial, 4 factorial times 3 factorial. That's 7 times 6 times 5 over 3 times 2 times 1. The factorial is 6 though, so the 6 cancels with the 6 and you get 35. Okay, here's a good question. Here's an important example. What about if I wanted to find the number of ways of picking at least 1 green marble? Well, that's going to be a bit more work because at least 1 green means I could pick 1 green or 2 greens or 3 greens. So here's how I would approach this. It's going to be 1 green plus 2 greens plus 3 greens. We already know how many ways they're picking 3 greens. That was all greens, which was 5 choose 3, which was equal to 10. For 2 greens, now we should be careful here. When we say we want 2 greens, we mean exactly 2. Meaning we want exactly 2 of them to be green and exactly 1 of them to be not green. So to get 2 green, we're going to say, well, we want of your 5 green ones, we're going to choose 2 of them. And then of your 7 not green ones, we're going to choose 1 of them. 5 choose 2 is the same as 5 choose 3. It's 10. 7 choose 1 is 7. So there's 70 ways of picking 3 marbles so that 2 of them happen to be green and 1 of them happens to be red or black. And for one green, well, of the 5 greens, we're going to choose one of them. Of the 7 red or black ones, we're going to pick 2 of them. 2 reds or 2 blacks or 1 of each. That's going to be equaling 5 choose 1 is 5. 7 choose 2 is 7 factorial over 2 factorial times 5 factorial. That ends up being 7 times 6 over 2, which is 42 over 2, which is 21. That's 5 times 21, which is 105. So the long answer to this question, which we're going to answer more shortly in just a second here, is 105 plus 70 plus 10, which is 185. Or, this is actually kind of an important example. This is an example of what's called kind of the complement, meaning instead of picking all the things I want, I can figure out how many total things there are completely and then subtract out the things I don't want. So instead of doing at least one green, another way of calculating this is saying, okay, calculate the number of total possibilities, meaning how many ways you can pick any 3 balls. And then we're going to subtract off the number of ways of getting, well, I don't want 1 green or 2 greens or 3 greens. I want no greens. All right, no question. Yeah. Sure. For this one here. So this choose notation. So here's what I would say. Let's go over here actually. So the reason we're doing this is if I say 5 choose 3. And let's say the green balls also have letters on them. Let's say that they're lettered A, B, C, D, and E. So if I want to know the number of ways I can pick 3 things out of 5 things, it's the number of ways I can permute 3 things. So let's do the permutations first. So for permutations, I have 5 choices for the first spot, 4 choices for the second, 3 choices for the third. That's going to equal 20. That's going to equal 60. But the problem is I'm overcounting by a lot here. And the reason that's true is because I'm thinking order matters, right? I could have picked the A green marble, the B green marble, then the C green marble, or ACB, or CAB, or CBA, or BAC, or BCA. And all 6 of these permutations count as the same combination. So this formula here, which is equal to 5 factorial divided by 5 minus 3 factorial, which is 5 factorial over 2 factorial. I'm overcounting, right? I'm overcounting by a factor of 6. I don't want all 6 of these permutations. I want one of these to represent all 6 of these. So what I need to do is take the number of permutations in total and then divide by the number of ways I can permute these 3 objects, which is 3 factorial. So the number of permutations is 5 factorial over 2 factorial. The number of combinations, again, of 3 things from 5 things, is going to be 5 choose 3, which is 5 factorial divided by 5 minus 3 factorial, and also divided by 3 factorial. So you're getting the permutations, all 60 of them, divided by 3 factorial, which is 6. So we end up with only 10 combinations. And again, just to make it super explicit here, the 10 combinations are ABC, ABD, ABE, ACD, ACE, ADE, BCD, BCE, BDE, and CDE. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For each of those 10 combinations, each combination has 6 permutations. So, right, you could have 6 things here, 6 things here, 6 things here. Oh, what's 6 times 10? It's 60 permutations. So for those 60 permutations of 3 things from a group of 5, there are only 10 distinct combinations. So again, permutations order matters, combinations order doesn't matter. So you almost should always have less combinations, meaning you should have more division when you're finding the number of combinations. Yeah. So back to this question here. To calculate this number of ways of getting at least 1 green in a different way, you can say, well, I'm going to calculate the number of total ways I can pick any 3 marbles. There were 12 marbles total, 5 green, 4 red, 3 black. So there's 12, choose 3 ways of picking any 3 marbles. I could get 3 red, I could get 3 black, I could get 3 green, I could get 2 red, 1 black, 2 red, 1 green, 2 black, right? Anything can happen. Everything can happen. And then subtract off the number of ways of getting no greens, which was 7, choose 3. The 7 marbles that aren't green, choosing 3 of those. Let's calculate and see what we get. Unfortunately, there isn't like a nice common denominator thing here. We just have to like calculate it. That's going to be 12 factorial over 9 factorial times 3 factorial minus 7 factorial over 4 factorial times 3 factorial. Let's see, calculating this out, we get, okay, so watch the work I'm going to do here. I know that 12 factorial over 9 factorial, that part's just going to give me a 12 times 11 times 10. And then the 9 and everything lesser cancels. And then the 3 factorial is 3 times 2 times 1. In a similar way, 7 factorial over 4 factorial is going to be 7 times 6 times 5. And then everything after the 5 gets canceled. 4 times 3 times 2 times 1. And the bottom is again 3 times 2 times 1. Simplifying, we get, let's see, 12 over 6 is going to be 2. And the 6 cancels here with that 6. So I have 2 times 11 times 10 minus 7 times 5, which is, let's see, 11 times 10 is 110, times 2 is 220, minus 35, which is 185. How about that? Got the same answer. So the point of this example really is to point out that when you're trying to calculate something, it is often easier to calculate the thing you don't want and subtract it from the total as opposed to calculating all the things you do want and adding them together. All right. What else? Let's see what we got here. Sure, I've never loved these examples. We should do some of that. Yeah. Okay, I've got other examples here, but I think we can, yeah, let's do. No, not you. Where'd you go? Yeah. Yeah, let's do one of these examples because I feel like this might come up. We'll see. So there's a concept that's called counting with dividers, which might not sound very like straightforward or like sensible, but it does make sense after you see an example. So here's some counting with dividers. You'll see what we mean in just a second. So let's look at the following example. How many ways can we select three donuts from, yeah, sure, from a supply of 3 varieties? Chocolate, glazed, and old-fashioned. Okay. So the idea here is kind of weird. You're trying to figure out how many of each you're going to pick, but it's not really something where you do like, well, I'm going to do like, it's not like you have an endless supply, right? It's not like there's only so many, it's not like you can do 5 choose 2 because there's only 5 glazed donuts or, whatever. So the idea here is you're essentially going to make 5 spaces. 3 spaces for the donuts you're picking, and 2 spaces for the dividers. Just watch. So, and we have to pick an order. The order doesn't matter. You just have to stick with it. So I'm going to pick the order. I'm going to go alphabetical. I'm going to say chocolate's going to be first, glaze second, old-fashioned third. So then, before my first divider, it's all chocolate. So I have to pick 2 places where the dividers go. So my dividers could go over here and I could have all chocolate. Or I could move a divider over and then have chocolate, chocolate, and a glazed. So everything to the left of the first divider is chocolate. Everything between the 2 dividers is glazed. Everything to the right of the second divider is old-fashioned. So then we keep going here. Okay, this is going to get a little tedious, but bear me out. We need 10 of these because 5 choose 2 is 10. So I can look where I can put the dividers. Just putting the dividers down. So that's all the ways I can put the 1 divider at the end there. And then I'm going to move over. I'm going to have 1 here, or 1 here and 1 here, or 1 here and 1 here. Or then move that one over again. 1 here and 1 here, 1 here and 1 here, 1 here and 1 here. So check it out. Let's fill in the chocolate, glazed, and old-fashioned. So just going from left to right, chocolates until you hit the divider, glazed until you hit the divider. And then no chocolates, glaze, 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 no old-fashioned. Chocolate, chocolate, no glaze, old-fashioned. Chocolate, glaze, old-fashioned. No chocolate, glaze, glaze, old-fashioned. Chocolate, no glaze, old-fashioned, old-fashioned. No chocolate, glaze, old-fashioned, old-fashioned. All old-fashioned. Well, the point of the whole process is that it exactly matters where the dividers go. And since there are 5 slots to pick from and 2 dividers to put in them, there's exactly 5 choose 2 equal to 5 factorial over 2 factorial times 3 factorial equal to 10 different ways of picking 3 donuts that have to be glazed, old-fashioned, or chocolate. So I can get all 3 chocolate, all 3 glazed, all 3 old-fashioned. Or I can get 2 chocolate, 1 glazed, 2 chocolate, 1 old-fashioned. Or 2 glazed, 1 chocolate, 2 glazed, 1 old-fashioned. Or 2 whatever, 2 whatever, right? And then you can have 1 of each. And this, I got all of them, right? So here are my all old-fashioned. Here's my all glaze. Here's my all chocolate. Here's my 2 chocolates, 1 glazed, 2 chocolates, 1 old-fashioned, 2 glazed, 1 old-fashioned, 2 glazed, 1 chocolate, 2 old-fashioned, 1 glazed, 2 old-fashioned, 1 chocolate, and finally, lastly, 1 of each. That's every possible combination. But writing all those out was kind of a pain. And I didn't need to write them out if I recognized that there's 5 slots to put 3 donuts and 2 dividers. And I really only care about where the dividers go. Because once the dividers are down, the rest of the thing is determined, right? Chocolate to the left of the first divider, glazed in between the 2 dividers, and old-fashions to the right. And if there's no space, you don't put any of those in there, right? That's why right here, like right here specifically, right, I didn't have any glaze because it was chocolate, chocolate, divider, divider, old-fashioned. So again, the point of this question is that we don't have to write all these out. We have to say, how many things do we want? Add in the number of dividers, which is 1 less than the number of choices, right? There's 3 types of donuts, and we needed 2 dividers. And then add those 2 numbers together, and then think about or write down the total number, choose the number of dividers you need. Let's do another example. Yeah. Right, and we just picked an order. So like as long as and really again, we're not even going to write anything down, to be honest. Excuse me. So yes, let's look at another donut question, and we're not going to write all this stuff down because it's going to be terrible to write down. So what if I wanted to pick Now we want to buy a dozen donuts, not a baker's dozen, an actual dozen, which is 12, from 4 varieties. We know that everyone in the office is cool with chocolate, glazed, old-fashioned, and sprinkles. So those are the 4 varieties we're choosing from. Maybe we're going to pick all sprinkles. Not a good choice. Maybe we're going to pick half glazed, half chocolate, right? We want to know how many ways can you pick any number of each so that you get a total of 12. It's going to be 12 of one, it can be 11 of one of another. It can be 10 of one of two others, or 2 of one other, right? It's a lot to count up. I don't want to count, 12 4 ways, and then 11 and 1 also 4 ways. Actually, more than 4 ways, right? Because it's 11 and 1, but there's 4 choices for that and 3 choices for that. So that's 44, right? This is going to get out of hand. I can't count these all up, but I can think about having 12 slots for donuts. And how many dividers do I need? I'm not dividing the number. So I will say the previous example did do us a disservice in that the number of donuts and the number of donuts I was bought, I should say the number of varieties and the number of donuts I was picking was the same. So we need the number of dividers to break up the varieties, not the number of donuts. How many varieties are there? How many dividers do I need? Right, I need 3 dividers. So I need 15 total slots. So 12 donuts plus 4 minus 1 dividers equals 15 spaces. And then we need to worry about where the dividers go. So the number of possibilities is going to be 15, choose 3. Out of our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 slots, I'm just picking where the dividers go. So maybe my dividers are going to go, here, here, and here. I'm going to have 2 chocolate, 2 glazed, 2 old-fashioned, and 6 sprinkles. But obviously, there's a lot of different choices that could be made. But we have counted them all because all we have to count is where you can put the dividers, which there's 15 places to put them, and we're going to choose 3 of them. And that's going to equal, let's see, 15 choose 3 is 15 factorial over 12 factorial times 3 factorial, which is just 15 times 14 times 13 divided by 6. Cancel a 3. Cancel the 2. You get 5 times 7 times 13, which is something. 5 times 7 times 13 is 5 times 91, which is 455. Okay. So a lot of ways you can pick 12 donuts. Now, are some of them not very sensible as far as a buying donuts perspective? Yeah, you'd probably do something like pick 4 of each, except that's too many. Probably like pick 3 of each, unless there's only one person that likes glazed. So you're going to get 1 glazed, and then you're going to get 4 chocolate and 3 old fashioned and 4 sprinkled, right? But any possibility, we have accounted for any possibility. All of one kind, a lot of one kind, evenly distributed, whatever you want, it's in there somewhere. Did we actually write them all down? Of course not. I'm not going to write down 15 slots 455 times. That'd be kind of a lot. Might as well, yeah. So 2 more questions to go along with this. We'll go bigger, and then so we're going to buy 1.5 dozen, 1.5 dozen. And now there's 5 varieties. 5 varieties. Which we won't distinguish all of them because we don't need to. but I will say the chocolate's in there because we're going to use chocolate in a second. So for 1.5 dozen 5 varieties, let's see, I have 18 donuts. I'm going to have 5 minus 1 dividers. So 18 plus 4 is 22. I have 22 slots. And I need to pick where the 4 dividers go. So the number of ways of buying 18 donuts out of 5 varieties is something crazy like 22 choose 4. Which I suppose we could calculate. It's 22 factorial over 4 factorial times 18 factorial, which is just 22 times 21 times 20 times 9 over 4 times 3 times 2 times 1. When you do this, I just like to cancel stuff. So like 20 over 4 is 5. 22 over 2 is 11. 21 over 3 is 7. So you really have 11 times 7 times 5 times 9. Whatever that is. We don't need to do that. Here's an interesting twist. How many ways to buy 18 donuts out of 5 varieties if we want exactly 3 chocolate? Well, really, you just reduced the problem, right? We don't really want to buy 18 donuts out of 5 varieties. We want to buy 15 donuts out of 4 varieties, and then also 3 chocolate ones. Do you see how we just have a lesser question here, right? We know 3 that have to be chocolate. There's 15 donuts left to purchase out of 4 varieties left to purchase from. So really, we want 15 donuts, 4 varieties. So that's going to be 15 plus 3 is going to be 18. Choose our 3 dividers. That's the number of ways. Wow. No, I'm not. No, I thought I was making a mistake. I'm not making a mistake. That's totally correct. I was thinking, how do they get 18 here when it's 18, but like, right, it's your number of donuts plus your number of varieties minus 1. Choose your number of varieties minus 1. Yeah, that works. So kind of an interesting twist on these questions. I'm not 100% sure he'll cover this in class, but it does come up occasionally. So yeah. All right. Friday, this is all we're doing, right? Friday, we'll probably start talking about probability, where we actually want to like calculate the likelihood of something happening. And I'll make a blanket statement is typically when we calculate probability, it's just really counting the number of ways of getting what you want divided by the number of total possibilities of anything happening. So like in our marbles problems, we could have phrased those problems as what's the probability of getting all 3 green marbles by saying, well, it's the number of ways of getting 3 green marbles, which was 10, divided by the number of ways of getting any 3 marbles, which was 12, choose 3, whichever that was. I forget what it was. I think it was like 200 and something. So it would have been 10 out of whatever that larger number was. That's how we start calculating probability. It's just saying the number of things that you want divided by the number of things that can happen. All right. All I got for today. Office hours as usual.